Welcome, dear learners, to the series of lectures on operational amplifier. And today we are going for the third lecture in the series. Myself, Orpon Deashi, from the Department of Electronics and Communication Engineering in RCC Institute of Information Technology, Kolkata, India, welcome you all to the lecture series on operational amplifier. So far, in the first two lectures, we have briefly discussed what OPAMP is, what will be the concept of virtual ground in a differential amplifier circuit, what are the different functional blocks of the operational amplifier, what are their functions, how they are correlated. And in the second lecture, I have discussed the equivalent circuit of a practical OPAMP, the different components which we have considered along with the ideal OPAMP, why they have considered, and what are the rules in order to design the operational amplifier. These are the major steps we have already covered. And in this connection, if you recall the earlier classes of the analog VLSI, where I have discussed the differential amplifier and its offset null, the same concept in this lecture will be discussed today with the prime objective that how this offset null can be nullified when an operational amplifier is made. So today, with the help of detailed mathematical analysis, I will show how the offset null of an ordinary differential amplifier can be adjusted. And if you recall the earlier analog VLSI classes, where I have discussed that the offset null generally arise because of the differences of the drain resistances, differences of the aspect ratio of the MOSFETs, as well as differences of the threshold voltages. So, keeping in mind of these crucial factors, today we are going to discuss the offset null, its effect, and how to reduce it, keeping the parameter constant, that is the stability parameter. That means when we are going to adjust the offset null by incorporating some passive components in the circuit, we should consider the stability of the circuit. It should not become quasi-stable or unstable while we are adjusting the offset. In order to discuss that, I am again showing the basic circuit of the differential amplifier, where I have shown the two fundamental resistances, that is the drain resistance R1 and R2. The output is taken as a difference of VO1 and VO2. The inputs are Vi and Vj. And the virtual ground point is the point P, which is shown in the blue circle at that point. So that's an ordinary differential amplifier that will be, and why the concept of virtual ground is already discussed. And if you recall the current mirror, what we have considered in the theoretical circuit, that is replaced by a MOSFET where drain and gate is shorted, so it will be naturally in the saturation condition because of the potential difference, and that means the current is constant, so naturally it will work as an current mirror. So we are going for a practical circuit, so I have represented this differential amplifier by 3 MOSFETs. So once I am getting this, the differential amplifier circuit, let me just go to the actual equivalent circuit of the OPAMP, which we are going to discuss now. Now we have 2 MOSFETs for the differential amplifier. So any MOSFET which is working under saturation condition should be represented by a constant current source, and naturally, according to the Norton's theorem, any constant current source should have a parallel resistance. So I am showing the drain resistances, which are R1 and R2, are parallel with the respective current sources. And obviously there will be associated capacitance, because if we consider the frequency model, the small signal analysis, that means for the large frequency signal or low frequency signal, but we have to consider the capacitances which are formed, and that should also be parallel with the resistances in conjunction. So I am getting two parts, the input parts and output parts. And naturally, the current mirror for a MOSFET will be represented by the product of transconductance multiplied by the voltage. Since in the input part, we have applied the input voltage Vin, so corresponding current, what is flowing through the current source, that should be GM1 into Vn. And GM1, obviously, by default, it should be the transconductance of one of the MOSFET. And since the second is dependent on the input side, so it will be GM2 into V1, where V1 will be naturally the output voltage of the first stage. And I am getting the V0 as the output voltage. So that's a very simple equivalent circuit of the operational amplifier considering the two MOSFETs. Now, if you have to analyze any Norton circuit, you have to take help of the KCL, as because you know that if we going for analysis of any Thevenin circuit, we have to take care of KVL, and that's very simple. That's from our basic circuit theory point of view, and there will be, I think, no requirement of the discussion up to this point. So based on the equivalent circuit, we should apply the KCL for both the input parts and output parts individually, and let's see what will happen. So I am starting with the output section. So GM to V1 is the current, that is the current source. The current flowing through the resistances will be V0 by R1, and naturally for capacitance it will be SC to V0. I think S equals to J omega, so it doesn't need for any mention, so I have not written that. And so based on the equation, if you write what is V1, so V1 from this equation you can simply calculate, and that will be naturally as a function of V0, and it should be, so V1 equals to some function of V0 multiplied obviously by some several parameters. So that will be our starting expression. So I have calculated V1 as minus of V0 by GM2, and the bracketed term which is given as in a box, that will be the effective impedance part between the relation of V1 and V0. So now I am coming to the input side. So input side is the GM1 into Vin, that is for one of the MOSFET. Current flowing through the resistance is V1 by R1, and similarly the capacitance effect is SC1 V1. And similarly now you have to find out Vin, and Vin you have to calculate as a function of V1. So if you calculate that, naturally you will get GM1 Vin equals to minus V1 into some parameter. And you have already calculated V1 as a function of V0 from the output part of the equivalent circuit. So if you put down the expression of V1, because V1 is not an actual parameter, it's an intermediate parameter you have considered for the calculation purpose. So if you substitute, then you will get Vin and V0 relationship, and you will get two similar parameters, look in the bracket, 1 by R1 plus SC1 and 1 by R2 plus SC2. So the transfer function, it should be V0 by Vin. As simple, the definition of transfer function is the output signal by input signal. So it will be GM1 GM2 into R1 R2 divided by 1 plus SC1 R1 into 1 plus SC2 R2. That simple algebraic calculation you can very easily put it, and you are getting this. So V0 by Vin, and you just open the bracket of the denominator and simply multiply. So what you will get 1, which is the independent of S. You will get S square multiplied by some parameters, and also S multiplied by some parameters. So it's very simple that it's an equation where S is not present at the numerator, but the bottom, that means the denominator, is a quadratic equation of S. So if I solve the denominator, naturally I will get 2 roots. It's very simple from our earlier school level classes of the solution of quadratic equation. So naturally I am just readjusting, because if I want to solve, S square should be independent of any coefficient. It should be multiplied by 1, and that will really help me, because I want of S plus minus alpha, S plus minus beta as product of these two terms, and naturally my objective is to calculate those alpha and betas. And you know that if you get such a transfer function, it's very simple that for S square you will get 2 poles, and that's you covered in your undergraduate courses of the control classes, control system classes. So you know what the things are, and naturally I am getting the transfer function in this big box. That's it's a simple equation, but I represent it in this format so that you will get a similarity. And what is that? That S multiplied by, say, 2 parameters alpha plus beta, and the constant part is exactly the product of those parameters alpha into beta. And what are these? That is 1 by C1 R1 and 1 by C2 R2. So these are the 2 parameters. And so V0 by Vin is GM1 GM2 by C1 C2 divided by S plus omega 1 and S plus omega 2. And everybody knows it, that omega is nothing but minus 1 by p. So it's very simple that getting the value of omega, it's 1 by p, everybody, we know it. So what will be p1, p2? Naturally, if we substitute in the equation, then p1 is simple, minus 1 by c1 r1, and p2 is minus 1 by c2 r2. So just go for your normal sigma g omega plane, where you have already accustomed in the class of root and locus, and you put p1 and p2 in the left half plane, because both are negative. So it's very good that you put it and you are quite assured that the system is stable. Is it really? If 2 poles come in the left half plane of sigma j omega, is it really stable? No. Normally we think that absence of 0 in RHP and presence of pole in LHP gives the system stability, but no. For a practical circuit, it's not the scenario. So what we have to think what will be the stability criteria of this circuit. There are 2 criteria. Please go through the criteria very carefully. The first pole should be very close to the origin. It should be. And the second pole, it should be far away from the first pole. That means, according to the diagram which we have shown in the last slide, that P1 will be very close to origin, and the distance between P1 and P2 should be as maximum as possible. Now let's go to the circuit parameters point of view. If P1 has to go very close to the origin, that means P1 should be very low. That means C1 and R1 should be high. Now the MOSFETs, what you have taken in the differential amplifier, both the MOSFETs are almost identical. So if C1 and R1 are high, naturally C2 and R2 should be high, because you can't make one drain resistance high, another drain resistance low. No, that will not serve the purpose of the operational amplifier. So if C2 and R2 are also high, What will happen? Naturally simple. The thing, it will go also close to P1. That means the gap between P1 and P2 will be very small. No, the system is not stable. It's marginally stable or it goes towards the instability. So the position of the two poles critically determine the system stability. And the present system is not stable. So what we will do? We have to satisfy the second criteria. And we can't change the differential amplifier circuit. So what was the only option we have? We have to insert some additional components in the circuit externally. And where we should include? Naturally, there is only one option. We can't disturb the MOSFET, so we should include the additional component as a capacitor, coupling capacitor between the first and second stage. And if we really include a capacitor, then obviously my analysis, what we have shown in the starting of this slide, the fundamental KCL equations, naturally those things will be changed. And how it will be changed? The output side equation will be added with another term, and that will be minus SCC V0 minus V1 plus SCC V0 minus V1. That's the effective voltage drop from the output side. So V1, that will be minus 1 by Gm2 into V0 by R2 plus SC2 V0 plus SCC V0. So V1 as a function of V0, the bracketed term is a impedance term, effective impedance term, but look at the denominator of V0. It is SCC minus Gm2. Similarly, if you start to analyze applying KCL at the input side, there will be another additional term, and the term will be V1 minus V0 into SCC. So if that happened, then Gm1 Vin equals to V0 SCC minus V1 into something. And we have already calculated V1 as a function of V0. The same procedure as shown in the previous mathematics calculation. The same substitution. And now you will get one expression between Vin and V0. Look, Gm1 Vin equals to V0 into 3 parameters, huge parameters multiplied. And so the version 1.0 of the modified circuit will give you a transfer function where look out how the symmetry occurs in the denominator. The S square, the coefficient is C1 CC, CC C2 and C2 C1 are all additive. Constant term is very simple, 1 by R1 R2. And the S term, C2 by R1 plus CC by R1 plus C1 by R2 plus CC by R2. So it's a beautiful symmetry that nature provides us. And if I analyze again in the same format, we will get a 0 at the numerator. If you may ask me question why, look, in the numerator there is a term S. So according to the root locus concept, we know that a term S in the numerator means presence of a 0, and we are getting 2 poles in the denominator because denominator remains the same quadratic equation. So if we plot it, the root locus, the Z0 is very close to origin. Why? Because the coupling capacitor will be much greater than the C1 and C2 naturally. So P1 will be minus 1 by Gm2 CC, it comes to origin. P2 will be approximately minus Gm2 by C2, C2 will be far away from origin. C2 is low. So that criteria is satisfied, but presence of a 0 close to origin. Now 1, 0. If you want to nullify, you have to give away, sacrifice one pole. So now you have a single pole. Is it stable? Effectively, you have a single pole in the circuit. No, sorry. It's not again stable. So addition of a coupling capacitor will not give the stability of the circuit. So what you have to do? Again, you have to modify the circuit, because the line which is written blue in color, that's the problem. The orange colors are quite satisfactory. The previous problem is removed. But we have to remove the problem which is written in the blue color. How we can remove it? Simple. We have added one resistance, coupling resistance, in series with the coupling capacitances and between the two stages. So we have two now additional components, CC and RC. So again, the output side equation, the version 2.0 circuit will be again bigger compared to the version 1.0. The term, look out, SCC by 1 by SCC RC into V0 minus V1. We will get at in output circuit. So again, the same procedure, you have to relate between V1 and V0, and once it's a much complex, you have to solve it. I have solved it in details, writing here. You have to solve it, and then again go to the input side. Another similar expression, naturally it will come. So you will get a relation between V1, Vin and V0. And Vin is the arbitrary parameter, that's the third party parameter we have considered for calculation. So V1 and V0, the relation is already established. So we have just replaced it, and look, GM Vin equals to V0 multiplied by 3 parameters minus V0 multiplied by another. So it's a gigantic expression, and you will get GM1 Vin equals to V0 into something like in this format. And because of you will get the transfer function, so calculate. You will get 3 poles and 1 0. The P1 will be very close to origin because CC is high. P2 will be away from origin, much away from P1 because C2 is low. And P3 is also away from origin because both RC and C1 are low. Now look, 2 poles, both are away from the origin, pole close to origin, and P3 can be easily sacrificed for the presence of Z. So now you are effectively getting 2 poles in the left half plane, which satisfy my earlier criteria that one pole should be very close to origin and distance between the 2 poles are very large. So now the system is stable. So we have removed the offset null parameter, the problem, and we are getting the system stability by introducing coupling passive components. One is CC, another is RC. So your stability criteria, the GM2 should be larger. RC should be less than 1 by GM2. You may ask why. Go back to that. Otherwise Z will be negative. P1 is close to origin. P2 is far away from P1. P3 also far away from P1 and can be sacrificed in order to nullify Z. So we are happy. This is a win-win situation. But effectively we have removed the offset null parameter problem. And this is the methodology by which you can really adjust the offset null of an operational amplifier. So based on that, in the next lecture, I will go for the different configurations of the OPAMP, and the analysis will be based on this similar, the Ruth Locus design. So the presence of the poles and zeros, that effectively determines what will be the signal path in an OPAMP based circuit. So wait for the lecture 4, and the previous lectures, if you have to brush up your knowledge, including this, will be available in my YouTube channel under the playlist Analog VLSI. So thank